सुहास
मुझे तो ऑन कर बेटा होस्ट मुझे ऑन कर ये ऑन कर दो ब्राउजर आप अका होस्ट मुझे मेल आकोस मुझे मेल आकोस बाबा त्यांच्या मेल आकोस मध्ये याहू मेल आकोस मुझे याहू या ब्राउजर आकोस को याहू मेल आकोस ते मेल असे मीटिंग ते नहीं आंगा क्लोज कर हां क्लोज कर
this is our screen
is it so तरी आंगा क्लोज केलं ते तीन ओपन असतात तळांगा एक असा दिसताय तुका पटलान ते ओपन असून एकच ओपन असाय तर त्याला
okay then I'll close this
लीव म्हणून केला प्रॉब्लेम जाता पता
but you have to leave
no 1 minute
hello Mike
tell me Suhas
it is streaming now
okay shall I stop sharing Royal Panda hello
Royal Panda Lingo Webex
I can't hear you anything
Royal Panda Mandekal
so it is streaming now yeah please whatever we talk all the viewers should be listening
नहीं अनेक के ऐसा संग मका ते लिंक केला मका अनेक मेळा जने बाबा
stop sharing now
stop sharing
there are two only one of these
हां आता लीव कर
here
लीव कर
wait 1 minute wait can see here is not even loading for you so it's better you just leave it
लीव कसे करते हैं आ दोन कडे ओपन आला कॅमेरा कन्फ्यूज होता
here it's loading so
त्याचे किती लोड जाता है पुढे आता अंगा कनेक्टिंग लीव करता आता एकच तसं अयो लीव केल्या मैं आता लीव केल्यानं तो दुसऱ्या असा घ्यांगा ना बाबा मीटिंग ना अंगाचा आता ये जे आता आंधे ऑन कर ते नका हाँ ओके बस नेक्स्ट पासवर्ड है C capital C
yeah I can start sir
yeah you can start no problem
yeah 2 seconds sir 2 seconds
sure okay
no we still have 7 minutes to has 5:30
yeah sure
now we are live when you are ready you can start sir
okay will we start exactly at 8 o'clock
yes sir because
yes, sir.
yeah
many
what do you
people
say
will join.
Ronald sir 5:30 is better isn't it
yes
here it's 5:30
another 7 minutes
okay so will you be giving an introduction or I just start the talk straight away
Ronald sir you're giving introduction Ronald sir hello sir Ronald sir he has muted his 1 minute sir I'll just call Ronald sir
yeah is it that you introduce and then I go or
yes sir will introduce you
okay.
Just hello sir you're going to introduce isn't it sir I can't hear you on this we'll wait yeah it's only 5:25 sir 5:30 we can start isn't it sir yeah I think most of them are yes I saw you now you disappeared sir you were there 5 minutes ago you were taking your phone I saw yeah I was able to see you now I can't see you I don't know whether you muted your okay sir hello sir Ronald, sir? Hello, Ronald, sir? I can't hear you. I can see you
Hello,
now,
can you hear
sir.
me?
Yes,
Can you
I
hear
can
me?
hear you and see. Yes, hear and see you, both.
Great.
So you
Great,
will introduce, sir, isn't it, sir?
Yes, I'm
5:30.
introducing.
We'll start in 5 minutes. It's only 5:25, sir.
Yes, we are starting.
Sure, no problem. I'll wait.
5:30.
I'll wait.
Somebody said they're unable to stream live videos. Who has?
मुझे फिर समझ
Sir, WebEx link was not sent to the participants. Ronald, sir?
Sorry?
WebEx link was not sent to the participants. Many people have asked.
Again,
That's why. But there are 900 participants. There is a limit in WebEx. That's why most of them are joining through live streaming.
It's not started yet, no, Suhas. Many people have written in the group on that web thing that it's.
Suhas.
2 minutes delay. There is 2 minutes.
Suhas.
Yes, sir. Yes, sir.
Please share now the WebEx link. Now you can share.
Yeah. I will share, sir. I will share.
Will you share in
so
all
that
the three groups?
Yeah.
So that the rest will join through this one. What is that? Live streaming.
Yes, sir.
Now you can share. Now you share.
Yes, sir.
You share in all the three WhatsApp groups, Suhas. Okay?
Yeah.
We'll start at 5:30. Nalini, if you have, you can also share that.
Yes, sir. I'm doing that, sir. I'm doing it.
WebEx link, you can share that.
Yeah. I've shared, sir. Yeah. I have for one group. The other two groups, I am not a part of it, sir.
Okay. I'll
join. Yeah. I have sent in one. If you forward it, also it's fine.
I've done it. Already done.
Okay, sir. Great. Another 1 minute is there. I think everybody wants to join on WebEx, sir, now.
That is the problem.
That's the problem.
And they don't know that
It's easier now.
Now they are writing thanks a lot.
Suhas is also forwarded. Now everybody's joining.
Yes. Now so many of them will join. Each one wants to join only through this.
Live. Sir, it's easy to ask questions also now, sir. Otherwise, in live streaming, you have to type. Sir, Gurrao, sir, they may type the questions, sir.
Okay.
Then we let, if you cannot, I can read it out or no.
Nalini, please, I will be asking them to write their question in chat box. Okay. So you please keep a watch. And those questions you can yourself can ask. Otherwise, simultaneously many people will start talking.
Absolutely, sir.
Ma'am, it is 5:30.
Yeah, we will because now many are joining now.
Yeah.
We'll wait for 1 minute. Should we start?
So they're still joining, sir. Another minute. Start, sir. Yeah, you can start, sir. We can start. I think it's already 5:31.
Yeah. So good morning, Professor Guru Rao.
Good morning.
Yeah, ladies and gentlemen, good evening to each one of you. On behalf of the Department of Chemistry, St. Joseph's College, Bangalore, I extend a very warm welcome to each one of you for this webinar. I'm really overwhelmed by the response to this webinar. A total of 960 participants from different parts of the world have registered for this webinar. A kind request to all of you to mute or disable the microphone. Disable it only if you are going to interact with him and ask questions. But I would suggest that you can post your questions on chat box. We will be asking those questions to Professor N. Guru Rao. Ladies and gentlemen, our distinguished speaker obtained his PhD in experimental sonography from Indian Institute of Science, Bangalore, way back in 1976. Postdoctoral from State University of New York at Buffalo, New York, United States of America, 1977 and 79. Then Roswell Park Memorial Institute, Buffalo, from 1979 and 81. He joined as a scientist at NCL Pune in 1982 and worked there till 1988. Then he was appointed as assistant professor in SSCU in Indian Institute of Science, Bangalore, in 1989. Then he was promoted to the to professor in the year 1998. So he is professor and JC Bose Fellow during this period and did research, especially between 2000 and 2017, and he did research and teaching in structural chemistry. He served as chairman and dean Science of Faculty of Indian Institute of Science. He continues to serve in Indian Institute of Science as honorary professor in solid state and structural chemistry unit.
Ronald, sir.
Yeah.
You're not clear, sir.
Because no, it is because people have not muted themselves. I request all participants to mute yourselves, please. Requesting all participants to mute. I request all participants to mute.
Excuse me, please yourself mute all, sir. Sir, yourself mute all, sir.
ಇದು ಒಂದು ನಂಬರ್ ನಾವು ಇಂಪ್ರೂವ್ பண்ணிருக்கேன் அது இன்ಕ್ளூಡ್ இல்லைன்றாங்க அது வேற நம்பர் கொடுக்கலாம்
You yourself mute all, sir.
ஒரு நிமிஷம் கொடுங்க சொல்லி கொடுக்குறாங்க
Mute. Host can mute. Host can mute.
Entry. Some people are unmuting.
Host can mute. Host can
I'm
mute.
muted on entry. Please mute yourself.
Yes, host can mute.
Yeah. I muted them on entry, but I think they have enabled.
So please mute all the audios.
Yeah. Hello? Hello? Can you hear me now?
We can hear you.
Yeah.
Yes, I hear.
Yeah, okay, fine. So, ladies and gentlemen, our distinguished speaker obtained his PhD in X-ray crystallography from Indian Institute of Science, Bangalore, way back in 1976. Postdoctoral research from State University of New York at Buffalo, New York, United States of America between 1977 and 79. Again, postdoctoral research in Roosevelt Park Memorial Institute, Buffalo, between 1979 and 81. He joined as a scientist in NCL Pune in 1982 and continued to work there till 1988. He was appointed as assistant professor in SSCU, Indian Institute of Science, Bangalore, in the year 1989. And then he was appointed as professor in 1998. So between 2000 and 2017, he was there working as professor, J.C. Bose Fellow, and during this period, he did research and teaching in structural chemistry. He served as chairman and dean science faculty of Indian Institute of Science. He continues to serve in Indian Institute of Science as honorary professor, solid state and structural chemistry unit. Also does research and teaching in structural chemistry. His major area of research is chemical crystallography and material design. He has obtained fellowship, membership of professional bodies such as Fellow of the Indian Academy of Sciences, India,
Please off the video. Dr. Krishna Naik, please disable the video.
Department of Chemistry, St. Joseph's College, Bangalore. And on behalf of all the participants, I extend a cordial welcome to Professor T.N. Gururao. Professor is addressing us from Buffalo, New York. It's morning 8:10 a.m. over there. He's actually in a different time zone. Ladies and gentlemen, I present to you Professor T.N. Gururao and request him to deliver his lecture on from minerals to futuristic functional materials. Once again, a kind reminder to mute your microphone. Thank you. Over to Professor Guru Rao.
Good morning from here, and thank you, Ronald, for the kind introduction. I would like to start by thanking the organizers, in particular Ronald, and also Nalini, who have been basically responsible for getting this webinar talk organized, and I'm grateful to them. I hope the connectivity will remain over the next 1 hour. And what I would suggest is that, as you see on the screen, the title of the talk has also my affiliation, along with my email address. In case you have questions, and then it is not audible enough for us to interact, please send me the email either on gururao@iascac.in or on gururao@gmail.com, so that I will be able to respond to your queries. I promise you that I will try to do that as soon as possible. With that introduction, let us start the seminar. The title, Minerals to Futuristic Functional Materials, is self-explanatory. So we start from something which is available in plenty on the surface of the Earth, below the surface of the Earth, and probably also from extraterrestrial sources, and try to adapt it and obtain in the future functional materials of various kinds. We will define what a functional material is as we go along. COVID-19 has separated us by long distances. However, interactions of this type is most welcome. And indeed, I would say that COVID-19, unlike wars, where we had First World War, Second World War, and so on, where it divided the countries, COVID-19 has successfully brought the countries together. And this is something where we really relish and enjoy under the circumstances which are given to us. However, let us hope that COVID-19 disappears as early as possible. Keeping the safe distancing, as has been advised and so on, will help us to solve this problem. In fact, I must say that I am blessed with the fact that I am located in a place which is more or less what one would imagine to be in. I am in a place called Amherst, New York, as you see from the pointer on the screen. And this is a small town in the city of Buffalo. It is just close to Niagara Falls. In fact, it's half an hour from Niagara Falls. And it is a wonderful place to live in. As you can see that these are the pictures which I took a couple of days ago when I went for my walk. This is the surroundings of the house in which I live in. Thanks to my daughter and son-in-law, they have accommodated us with all facilities given to us, and we are comfortably seated here. Right. So let's begin the discussion. What are materials? Materials, of course, has become a common part of everyday life. It's an important role in everyday life. Manufacturing advanced materials becomes the goal and the challenge. Materials with augmented functionality on one hand and more than one degree of functionality on the other is what we seek after. In fact, this is something which we will discuss as we go along, since we would like to get materials and manufacture materials which will show more than one property. And at the same time, always look at reduced costs and ease of access to procurement and availability. The most sought after materials, as was listed in the last year in the materials panel, are the electronic polymers, fuel cell materials, semiconductors, magnetic materials, ferroelectrics, and so on. So there is an overall requirement for manufacturing materials and then make it available to mankind. We cannot have a life. In fact, we could not have had this lecture if there were no material support. The materials that are involved in this are very many. We have the laptops, we have the mobile phones, we have the connectivities, and so on. We also have the voice connections coming through. All these are through various types of materials which belong to these class of materials. And therefore, it becomes essential to get and manufacture materials at reduced cost and also make it available very easily for mankind. In this context, I would like you to recall that the earliest known functional material were the stone tools developed by early man. And the tools were also developed for the requirement of mankind. They were developed essentially to hunt, and it was for food, both from the mineral, both from the animal as well as from plant sources. So the functional materials were, in fact, rocks, and these rocks are essentially minerals, as we notice now. And this was 2.5 billion years ago. The tools were also used to structure the materials. For example, these materials were used in construction in ancient Indus Valley civilization, and the structured materials decided to build huge buildings and so on, which still survive the test of time. There is something which has appeared on the screen. I would approve it. No? Yeah. So the are you all listening to me properly? Is the connection okay? Ronald, are you there?
Yes, sir, it's fine, sir. It's fine.
Okay, thank you. So the functional materials, by definition, if we look at the webinar, the functional materials are materials that have one or more properties. And these properties can be significantly changed in a controlled fashion by application of external stimuli, temperature, electric magnetic field, etc., and are therefore applied in broad range of technological devices. So one could develop memories, one could develop displays, one could develop telecommunication devices, and so on. So these therefore are now referred to as functional materials. So in short, if I summarize this slide, functional materials were found way back in 2.6 million years ago by early man, and then they were converted to structured materials during the construction process. And then these materials now can be significantly changed and controlled by external stimuli. It could be temperature, it could be magnetic field, etc. So considering this aspect, we can go to the next slide, where there is a lecture which was given by Professor Juster, who essentially related material science to various branches of science. He related to geology, which of course comes under mineralogy, physics, biology, and chemistry. These get related to material science. And the properties which we can obtain from these refer to pharmaceutical applications, medicinal applications, chemical engineering, mechanical engineering, and electrical engineering. So essentially, material science relates to these aspects. What we have done in our group, I think I will straight away go to the topic of interest. What we have done in our group over the years is to go to generate functional materials, and we have used techniques like in situ crystallography and Raman spectroscopy. I would like to keep in mind that the participants have undergraduates, graduates, and research scholars, as well as senior professors and so on. And so I will try to make this talk as simple as possible so that the undergraduates will also appreciate the talk. So I will keep in mind the aspect that it has to be at a level which appeals to all walks of life in general. So if we if we now consider the work which we are doing in our group over the last decade or so, we have worked on functional materials. We have used two techniques basically, in situ crystallography and in situ Raman spectroscopy. I will briefly describe these techniques without going into the detail of it because of lack of time. However, the types of materials we have been looking at and trying to develop are the materials which are used in SOFC materials, lead-free molecular ferroelectrics, understanding hybrid perovskites, proton conducting materials, and we have done some high pressure studies and fast ion conduction in sodium-based materials. Since this talk is on minerals to functional materials, I thought that we will take up the issue of this aspect of our research. So hereafter, I'll be concentrating only on this part of the work which we have done. So let us look at materials which are fast ion conducting, and these are sodium-based materials. And we are looking at the property of fast ion conduction. There's something else which appeared on the screen. I'll just try to minimize. Okay. Sorry about these interruptions because some things are appearing on the screen which should not appear. And so I have to minimize this. Let's go now into the topic. So fast ion conducting sodium-based minerals will be the topic which we will discuss today. And what do we mean by fast ion conduction? And in what way this conductivity is important as functional materials, and how we generate these materials from minerals will be the topic of our study. The requirement of modern engineering is to store energy. So large-scale storage and harnessing of energy is what is required, and solid electrolytes are the first choice materials because these minimize environmental pollution. The last year's Nobel Prize winner has written a wonderful article in the year 2015, which is listed below. And this is a very general article which talks about the requirement of energy storage materials. So large-scale storage and harnessing of energy is what we will concentrate on in this part of the talk. The fast ion conducting inorganic solid electrolytes, they are approximately 10 to the minus 3 to 10 to the minus 1 Siemens per centimeter. That's the expected conductivity range in the temperature range of 400 to 600 degrees centigrade. These then get referred to as fast ion conducting inorganic electrolytes. And these are essentially battery materials. And for example, the lithium ion containing solid electrolytes in batteries uses these kind of systems with lithium as the element. The advantage of lithium is that it has a small ionic radius and a high energy density. One of the limitations, however, is that it has limited terrestrial resources. The safety and cost is another concern, and lithium is slowly disappearing from the surface of the Earth. In fact, making lithium batteries will become more and more expensive, and at the same time, it is becoming a safety issue, and as a consequence, it has become an expensive proposition to stick with lithium-ion batteries for the future. There are lots of people who have joined in this webinar, I'm sure, who will not agree with this statement. But essentially, we will soon run out of lithium, maybe in the next 50 years or so. So lithium-ion batteries have to be replaced. The next obvious choice in the periodic table of elements would be the sodium. And the sodium-based materials are available in plenty. In fact, the ratio of lithium to sodium is 1 to 1000. So we have 1000 times availability of sodium. And this has already been demonstrated that solid electrolytes can be manufactured using layered oxides of sodium ions. Nasicon is an example, and very recently Na3PS4 has been shown to be a very high quality first choice solid electrolyte. We have been looking at these materials for almost a decade now, and Teuton salt, leonites, trunkites, or bimetallic sulfate minerals. These are available in plenty in nature, and they have a general formula A2BSO4 twice XH2. And we would like to see I think people are still joining, so the change of slide is slowed down. I'm sorry about this because it's very slow in changing the slide. It's something to do with connectivity, I suppose. No. Yeah. Okay, this talk is becoming a little bit fragmented because of the fact that the slide changer is not working as smoothly as I would have liked to work. However, I'll try to bring the link. I suppose you are all with me. And Ronald, is it going all right?
Fine, sir. Fine, sir.
The problem is the slide changer is going very slowly. And as a consequence, the continuity is getting lost. I'm sorry about that, but I'll try to do as best as possible by talking. My talking is coming all right, right?
It's all right. Yes, sir.
Okay. So I'm sorry, the connectivity is the issue. So when we think about terrestrial sources and we think of materials, the first thing which occurs is the fact that how minerals evolve. In fact, if one looks at the evolution of minerals, it makes a very interesting study, and the work of Robert Hazen and others. The article appeared in American Mineralogist in the year November 2000. In November 2008, which essentially starts by telling how the evolutionary process came. This is the Cambrian age. The origin of life started around 4.5 billion years ago with the presence of elements, hydrogen, carbon monoxide, etc. Then the bacteria came in. Then we went through the photosynthesis process, eukaryotes, Cambrian explosion, and so on and so forth. So essentially, the age of the Earth could be about 4.5 billion years. That's what was basically estimated. The contribution of Robert Hazen has been essentially to look at mineral evolution. How did minerals evolve? The minerals evolved in sequential stages. It arises basically from 3 primary mechanisms. The first mechanism is the progressive separation of the elements from their original relatively uniform distribution in the precellular nebula. So essentially, this is before the solar system formed. There were concentration of elements, and the increase in the range of intensity variables such as pressure, temperature, etc., produced different kinds of compounds. One of them is, of course, oxygenation, and then carbon dioxide automatically, and then, of course, water, which is what is of interest to us today. We will see why water is of interest to us today in generating functional materials from minerals. The generation of far from equilibrium conditions by living systems also essentially allowed for the mineral evolution. Essentially, the changing atmosphere and ocean chemistry ultimately gave rise to multicellular life and skeletal biomineralization, and biochemical processes may thus be responsible directly or indirectly for the mineral species. 4,000 and odd mineral species are available on the Earth's surface, which have been recognized so far. One of the biggest advantages with minerals is, unlike biological species, each mineral species is defined by its characteristic chemical makeup and the crystal structure. So we can define mineral hydration in an inorganic chemical reaction where water is added to the crystal structure of a mineral, usually creating a new mineral, which is called a hydrate. The process is, in geological terms, is referred to as mesotomatism. So essentially, we are now looking at mineral hydrates. One of the things which is of current day interest is that materials in nature, whether organic, inorganic, biological, microscopic or macroscopic, have their own chemical and physical properties, which strongly depend on their atomic structure. This can be studied by various techniques, and the techniques that are available are the in situ crystallography, variation of pressure and temperature to study materials which are crystalline, and generally materials which are also polycrystalline, and in situ Raman spectroscopy for all kinds of materials, and electron microscopy and property of ionic conductivity with temperature. These are some of the issues which we will address with using these techniques. So essentially, materials description can be achieved at an atomic level, or for that matter at a molecular level or an ionic level, by looking at the crystal structures and through in situ Raman spectroscopy. We have been looking at two possibilities, and this is where the actual talk begins. So far has been the basic introduction. It's going in the right direction, I suppose. So we have a two-pronged approach. One is, of course, procure the materials, minerals. The minerals can be synthesized, and the structural analysis of minerals can be carried out, and their precursor phases can be identified. This leads to the understanding of the phase behavior of many minerals, and we can get into the clues into the mineral evolution pathways. And this becomes very important from the mineral evolution point of view, because we can now get a connection between the phase relationship between terrestrial as well as extraterrestrial material. Particularly from the space research point of view, this will be a very important issue. On the other hand, if we now look at the phase modification of minerals, these modified minerals will lead to the discovery of new materials, making structural changes in the existing minerals to convert them into materials of interest. So here we consider the formation of fast ion conductors, ferroelectric and ferromagnetic materials. So what you see is that it is not necessary that we should go into very sophisticated nanomaterial synthesis and so on for generating functional materials. It is okay with a bulk material like a mineral. So it's what I would say a poor man's approach. So we can take a mineral which is available in plenty, either from the surface of the earth or from under the surface of the earth, or from any extraterrestrial source, modify this mineral structure using variables like temperature, pressure, etc., and generate new phases. And these new stable phases can now generate fast ion conduction, ferroelectricity, or ferromagnetic materials, and so on. So essentially, we arrive at functional materials. And this is the idea. So we have, therefore, a two-pronged approach. One is to understand the phase behavior in minerals, and the other is to modify the phases of minerals leading to new materials. So we'll start by looking at various aspects which control this and the way in which we can essentially generate these materials. So temperature, pressure, and amount of hydration, sometimes even fractional, will be the considered aspects. So minerals have this issue of formation at very high temperatures and very high pressures. At the same time, they also have the presence of water when they formed the minerals. And therefore, the temperature, pressure, and the amount of hydration will generate phases required for mineral formation. This will also lead to the origin of minerals. The in situ, excuse me, in situ variable temperatures, X-ray diffraction experiments on hydrated bimetallic sulfates are the procedures with which we will follow to obtain the various stages of phase generation. One of the things we achieved was the first observation of a remarkable phase separation resulting in a single crystal to single crystal transition, accompanied by a polycrystalline phase. It is also important to note that hydrated bimetallic sulfates resulted while trying to synthesize isostructural compounds of Na2CdSO4 twice. The reason why I mentioned all this is because of the fact that about 10 years ago, I had a student by name Deeptikanta Swain. He was a person who essentially showed interest in doing phase transitions of minerals. It so happened that I found out soon that his interest to do this work was essentially to get more time to play his football. So most of these materials which he generated actually crystallized over a large amount of time. It took about 2 to 3 weeks to get crystals. And in those 3 weeks, he played football. But what is essential is he generated very interesting materials. The first material he generated was the Na2CdSO4 twice. It turned out to be a promising fast ion conductor 10 years ago. And then we wanted to synthesize isostructural compounds. And when we wanted to synthesize isostructural compounds, we found that the presence of sodium sulfates with different minerals are there in polycrystalline phase. And therefore, the first observation of remarkable phase separation was also identified by him. I hope the voice is coming quite clear because I do see a bit of a background noise which is coming back to me. I hope it is okay. Ronald, are you okay?
Yeah, okay, sir.
It's okay, sir.
Yeah,
So how are these materials made? The single crystals of he made 2 minerals of A2BSO4 twice. And the way it was made was to take sodium sulfate, Na2SO4, mixed with MnSO4 in aqueous solutions. And he kept this at 80 degrees in a furnace for 15 days, resulting in the formation of this mineral. You see that it is a non-stoichiometric ratios of elements, and this is very interesting because it is the non-stoichiometry of these elements along with the presence of water which will allow for the possibility of the generation of new phases. This we realized as we went along in our research over the last 10 years, as you see that this reference goes back to 2009. So analysis of variable temperature in situ single crystal diffraction of both these minerals were carried out, and because of lack of time, I'll cover only one of them in full detail. So this is where I think I will try to make the lecture more popular, in the sense that we now are for the undergraduates and graduates who have logged in, it is essentially a situation where we take a mineral. We either make it in the laboratory by the procedure which was described, very simple. Take the starting materials, take my aqueous solutions of these starting materials, dump them in a furnace, keep at 80 degrees, keep it over a couple of weeks, then look at it and you will have the mineral formed. So very straightforward. And the class to which this particular compound belongs are the cronkite minerals. And these cronkite minerals are available in plenty in the surface of the earth. So we can extract these minerals. They will have different kinds of metals content in them. Instead of manganese, it could be cadmium, it could be iron, and it could be cobalt and so on. So different kinds of sources are available. So all these belong to the class of what is known as a cronkite mineral. So we take this compound and subject it to DTA studies. DTA is differential thermal analysis, thermal gravimetry. It is actually TG, which is shown here. The thermal gravimetric analysis essentially sees how the compound decomposes as we heat the compound. So when we reach a temperature of about 180 to 190 degrees, you see this particular compound undergoes a change. It loses 2 water molecules, and then it goes to a phase which is very stable. And then we wanted to determine what is the nature of this phase. In this case, this is where the excitement comes, because the nature of this phase is very, very unique. It is so unique that we will see it when we do the X-ray diffraction experiment. So the X-ray diffraction experiment is performed on a single crystal. We go single crystals of these materials, select a suitable single crystal, put it on the diffractometer, and then adjust the temperature. So we can now control the temperature. So we heat the system, heat the crystal on the diffractometer. So it's in situ X-ray diffraction. And as we go along, we check the nature of the material. Since we have this evidence from the thermogravimetry that at around 180 degrees, there is a change of phase. That means there is a phase which is going from this compound to some other compound. What is that some other compound which we get? When we look at that on the machine, we see for the first time we saw a remarkable structural phase separation. The phase separation occurred with one phase showing a single crystal to single crystal transition. These spots which are seen here show the nature of the single crystal. And the spot we see here are the nature of the single crystal which formed after the phase transition. So this is the high temperature X-ray data. And what is shown here is the reciprocal lattice image as we record the X-ray diffraction pattern. So the original pattern has this diffraction. And when we heat it to over 180 degrees, in fact, we went to 500 Kelvin. Notice that we are now talking in Kelvin. 500 Kelvin, we get this remarkable phase separation. So it is possible, therefore, to identify these individual spots and then determine what that structure is. And this was the job which was done a decade ago. And what was found was that there is a remarkable phase transition. This is the original crystal structure. It belongs to the space group R3 bar. We will not go into the detail of it. I'll say essentially that this structure, which has the water molecules surrounded, the green ones here are the water molecules. And these water molecules get eliminated. The 2 water molecules go away at around 500 degrees. And there is a new phase, which is a single crystal phase, which is obtained with this particular structure. The structure becomes Na2MnSO4 twice, as was established later. And this is a structure where you see the sodium atoms are more or less free, and they develop in the form of a channel. And so we perceive that this could be a sodium ion conductor. The polycrystalline phase was identified by powder diffraction studies as MnS2O7. And this is something very unique because MnS2O7 does not occur in nature as such. So obviously MnS2O7 was found during the mineral evolution. So effectively we can also trace the path. If we reverse this path, take these two, create the temperature and pressure conditions which were existing in the terrestrial condition of those days, we would have formed this mineral. So there are 2 issues, the 2-pronged approach. We see how the mineral formed, and we also see how the mineral separates into 2 different phases. What is the advantage? The advantage is that we have generated a new functional material. This could have been very easily got in the laboratory by trying to synthesize this compound, which was also tried. I will describe that in the next few slides as we go along. It is not so very easy. So the separation of the mineral to two different phases is the easiest approach to make this new functional material. You will see how it happens. What is very important is that the structural phase transition can be explained in terms of crystallography as the variability in the symmetry directed pathways. That is when the system R3 bar, which is a rhombohedral system, the rhombohedral system has a symmetry pathway which it takes to go from single crystal to single crystal transition, and we get this symmetry directed pathway leading to the compound which is Na2MnSO4 twice. Now, I would like to go through the details of this because unfortunately I see the time is running out. So we will go a little faster. If anybody has any questions of what is meant by symmetry directed pathway, I would like you to send me an email to that effect. Now, is it possible to form the mineral by taking sodium sulfate and cadmium sulfate and then dissolve it in water and see what comes out? What comes out is Na2CdSO4 twice. We will not be able to get to the mineral by this approach. This is very intriguing because we just made a statement in the previous slide saying that the combination of this will give rise to the mineral with MnS2O7. So the presence of MnS2O7 therefore is very essential in order to make the mineral. In other words, what is the way in which we can make this material? We have to now therefore look for a situation where the sodium cadmium sulfate can be converted to the mineral. Can we convert this Na2CdSO4 to the mineral? So this is the first pronged approach. I told you there are two pronged approaches which we follow. The first one is the one in which we go to the mineral formation, look at the mineral evolution. So can mineral evolve from these two precursors? Certainly it cannot, because as we see from the laboratory experiment, even after very long exposures, we prolonged stay in water, it will not pick up the water molecules. So what is the procedure? What we found out was that if we take the sodium cadmium sulfate, the phase 1 as I call it, and we heat it up to 570 degrees, and then suddenly quenched in liquid nitrogen, we get to a different form of Na2CdSO4 twice. And this we call as the phase 2. And this, when exposed to atmospheric moisture, will form the mineral. So this is a remarkable pathway. You see that in the previous case, when we take the mineral and look at the phase separation, it separates into Na2CdSO4 and also gives us the MnS2O7. The presence or absence of that MnS2O7 is generated by this second kinetically stable precursor, and therefore we get this kinetically stable precursor, as we call it. So that energetically it exists at a high energy state, so naturally it will not occur at that high energy state, and the high energy state now converts to a mineral. The X-ray diffraction patterns are very clear. If we take the red pattern after heating about 540 degrees, this goes to the so-called alpha phase, the monoclinic phase of sodium cadmium sulfate, and the beta phase of this, which is the room temperature phase, as we can call it. This is formed after quenching in the liquid nitrogen, and that gives rise to the beta phase Na2CdSO4. The structure of Na2CdSO4 also presents a very nice possibility of using it as such as a mineral choice for sodium ion conduction. That's a different story. Suppose we take the mineral and heat it up. When we take the mineral and heat it up at 133 degrees, it loses the two water molecules. And at 540 degrees, as we saw, it undergoes a quenched mineral. And when we cool it back, it goes back to the so-called alpha phase. So the quenched mineral is definitely the alpha phase. And this can be established by a series of studies using powder diffraction. The technique called profile fitting will establish the structure. And what is more interesting is that what is the behavior of ionic conductivity? As we heat the system, we are 280 degrees centigrade. It suddenly changes to a higher conductivity. And at around 550 degrees, we see that it goes towards a superionic conduction. The technology with which we would like to describe this is that the sulfates that are involved in the structure, they get freed and they become what we call as rotational sulfates. And as a consequence, the sulfate atoms become free, and therefore the condition at which this sorry about that, something happened here. Ronald, is it going okay?
It's going on fine, sir. It's going on fine.
People are able to listen properly to the talk, or is it?
Yeah.
Okay, because I have another 15 minutes to left.
Yeah, sure.
Can I take the 15 minutes, or is it not going on?
Please.
Okay. So the story at this particular point, I'm sorry about these interruptions because the connectivity appears to be very, very poor from my side for some reason. And I'm having difficulty in conveying the message and showing slides properly. What I would suggest is that I will share the slides with Nalini later on, and it will be made available to you. And maybe I will give a separate talk later, and then the recording can be made available. I think that is probably the best choice, given the way in which the connectivity seems to be going. Okay. So we take the mineral and heat it up at 133 degrees. It loses 2 water molecules. At 540 to 554, there is a phase transition, which takes it to the alpha form of sodium sulfate, which then now remains the alpha form of sodium sulfate, gets converted at 475 degrees again on the cooling cycle, and remains alpha CNA2CdSO4, a functional material which can be used for sodium ion conduction. The further studies of this clearly show that the ionic conductivity associated with this will generate a superionic conductor. We did further studies with the Electra source, and we find that the reason for superionic conduction in these materials comes because of the fact that at 600 degrees, there is at around 500 to 600 degrees, there is another phase transition, which actually generates what is known as a gamma phase. And this gamma phase is the one which essentially gives us the superionic conducting phase. So in a nutshell, the mineral, which was at 25 degrees, now became a possible functional material at 600 degrees, with its conductivity going to 10 to the minus 1 Siemens per centimeter. So this effectively generated, this is the phase correlation, Na2SO4 heating to 150 degrees. We'll go to at 560, it goes to gamma phase. And when we gradually cool it to 25, it comes back to the alpha phase. We can also generate the beta phase by quenching in liquid nitrogen. And that beta phase now on heating goes to alpha phase to 285 degrees. And then a few weeks of exposed to moisture, we come back to the concrete phase. So this is the full pathway. So we have the mineral generating the functional material the way we have analyzed in the last few minutes. There's the structure of that compound. I will not go into the detail of it. I'll go to the next example, which is a more recent example. In fact, it has just appeared in print. This is the study of what we call as the Wantafite minerals, a superionic mineral at 570 degrees centigrade. So this is the conductivity plot of that. Let me go through this full detail. So Wantafite minerals are minerals which occur in abundance in oceanic salt deposits. These are essentially belong to the family of Na6M SO4 4 times, where the metal can be magnesium, manganese, iron, cobalt, nickel, zinc. All these form the family of Wantafite minerals. So structure of these hydrated and anhydrous forms suggests the possible formation of sodium ion migration channels, just like we discussed before. And so if we take the sodium sulfate and cobalt sulfate with excess water in the aqueous solution at 80 degrees, we can crystallize this mineral. The mineral grows in a very interesting way. The mineral goes in the form of crystals. All these crystals are very high quality crystals. And they generate what we call as a concomitant growth. They grow 2H2O as well as 4H2O together. It so happens that the color and the morphology of the two are one and the same. And as a consequence, it is essential that we separate the X equals 2 from the X equals 4 crystals. This is a famous, very difficult job, and it was done over the X-ray diffractometer. And we had to take in each and every crystal and measure the crystal structure, or in fact, at least get to the cell dimension, which told us whether it is a 2 H2O or a 4 H2O. Let me explain that a little more. See, there are crystals formed with 2 water molecules and 4 water molecules. And they all are identical in morphology. So just morphological separation is not possible. So we have to put each one of these painstakingly separately and check the X equals 2 or X equals 4 on doing the X-ray diffraction experiment. The X-ray diffraction experiments clearly suggest that the 2H2O and the 4H2O have sodium ion coordination in these compounds, which essentially can be used to generate a functional material at a higher temperature. These are the structures of the 2H2O and 4H2O. And this is the gravimetric analysis. So when we take the compound and heat it up, it loses the so-called surface water that is referred to as the first transition stage, where the crystals will have some amount of moisture which are condensed on the crystal. And once that goes away, the second stage, the temperature at which the 2 water molecules go. So the compound essentially from 4H2O completely converts to 2H2O. So we can study the structures of these compounds at 2H2O and 4H2O. And then we go further at the third stage, where it loses the 2 water also. And now it becomes an anhydrous compound. So we have the mineral, we lost the 2 water molecules. And then we got to the stage where it is X equals 2. And then we lose 2 more molecules, it becomes X equals 4. So if we go back and see the structures, we see that it is Na2, Na6COSO4 4 times X, H2O. So if we take the compound, which is 4H2O, identify it with the crystal, and then heat it to a temperature of somewhere around 180 degrees, it loses the two water molecules. And then at, somewhere around 120 degrees, it loses two water molecules, becomes 2H2O. 2H2O remains stable for a certain period. And then it loses the other two water molecules and goes to the anhydrous phase. Now, therefore, we have three different compounds. One is 4 times the water molecule, which is the 4H2O mineral. Then we have the 2H2O mineral, and then we have the anhydrous compound. The anhydrous compound is a material which is available for a superionic conductor. As this is clear from the DTA as well. At 450 degrees, the stable compound shows a phase transition, and we will see what happens at 450 degrees with respect to ionic conductivity later on. We also see that on the cooling cycle in the DSC, the original compound, that is the compound which is anhydrous, comes back and stays to room temperature. So we take the mineral, heat it up, lose for two water molecules and two other water molecules, get the phase which we would require, heat it to 450 degrees, get the superionic conductor. The superionic conductor now becomes a normal ionic conductor, and on cooling, it goes to room temperature. So here is the situation. We have a reversible phase transition, and this is very interesting to observe. So this reversible phase transition is the one which is essentially taking us to a situation where we therefore have reversible superionic conductors. And this is something very interesting. So we can follow it up by the X-ray diffraction studies. We heat the compound, we lose 4 water molecules, and then we lose the 2 water molecules after heating to 120 degrees. And then after heating to 180 degrees, we get the phase which is the anhydrous phase. And this is indicated in terms of the cell parameters, in terms of angles, and in terms of volume when we see the X-ray diffraction. The structure of the anhydrous sample has been determined at the high temperature structure, and that happens to be this. We see that again we have the sodium ion channels. So this is the conductivity behavior. As you see that on heating the sample, it loses the surface water, and then it goes from at around 120 degrees, it loses 2 water molecules, goes to 2H2O, and then it loses all the water molecules, goes to this particular temperature at which we have the phase transition. The phase transition takes it to a superionic conductor. So the conductivity value now becomes 10 to the minus 2 at very high temperature. This has been also followed by Raman studies and also from in situ powder diffraction. We have done the in situ powder X-ray patterns at 480 degrees and 600 degrees. The essential changes in the structure are observed here. So the structural changes essentially facilitate the superionic conduction in these materials. We have also studied this in terms of Raman shifts. These are the Raman shifts, nu 1, nu 2, nu 3, nu 4, as they are shown here, are due to the sulfate ions. The sulfate ions now, as we keep heating the system to 530 degrees, you see the broadening of the peaks. The broadening of the peaks essentially tells that the sulfate ions are now becoming more free, and more free, and they are able to make a rotation. And therefore, they are no longer in connectivity, they are making a rotation. And as a consequence, sodium ions are very free to move about. And therefore, we have a superionic conducting material that gets generated. We see that temperature evolution in the full width at half maximum of these stretching frequencies. And you see that these 3 phase transitions very clearly suggest the formation of this material. So with that, I come to the conclusion of the talk. I'm sorry that it went back and forth, on and off, because of the connectivity essentially. It has nothing to do with my throat. My throat is fine. Somehow the audio is not going properly. I don't understand why it did not go properly. And some people are asking me on my WhatsApp whether I'm okay or whether I'm doing fine. I'm perfectly in good shape. The voice is actually coming back to me. That's why this problem. and you will probably be hearing two different voices coming from this side. I don't know. So I'm sorry about that. So in conclusion, the ubiquitous substitution of sodium ions by rare earths of naturally occurring sodium ion conducting terrestrial, maybe we could include extraterrestrial as well, minerals establish these materials as a natural choice for the futuristic design of sodium ion batteries. Opportunities for replacing sodium ions partially or fully by rare earths. This is something which we are now going to take up. Lanthanides and other elements would pave the way for the design of futuristic multifunctional materials. So the idea of generating futuristic materials from minerals is very clearly established over these studies. I have covered only two compounds, but I must say that over the last 10 years, we have studied at least 20 to 30 different materials. We have actually followed the conductivity pathways. And it is very clear that we can start from a mineral and get to a material which is going to be a superion conducting material, particularly sodium source. It is abundantly appealing to note that early man's choice of rocks is now becoming the choice of the design for futuristic functional material. With that, I think I have taken the time that was allotted to me, and therefore I will end this talk by showing that the diversity in mineral sources, it is like Aladdin's lamp. So you can rub the lamp and get what you want. And you can generate, therefore, from the mineral source, and we have plenty of minerals available on the surface of the earth and also available abundantly in different parts of extraterrestrial space. In fact, this is something which is futuristic in all respects. So I would like to acknowledge Deeptikanta Swain, whose most of the work described here is from his work. Dipankar Saha, Sajesh Thomas, Vaishali Sharma also participated in this work, and my current student Ajana Datta, who is now continuing this work. And one of the things which we, as I mentioned, we are trying to substitute sodium partially by other elements such that we will generate the required functional material. I would like to also thank Nalini Sundaram because she started the work of minerals in my lab by working on the structure of langbenites. I don't know whether she remembers it or not now, but her PhD work contained something to do with the phase transition in langbenites. And I also thank my colleagues, Giridhar Madras, Aninda Bhattacharya, and Chandrabas, with whom I continue to collaborate over the coming years to do this kind of work. I thank IASC STC project because the space technology cell was very much interested, particularly from the extraterrestrial point of view, and I had got some funds from them. JC Bose Fellowship, and currently now I am an senior scientist. IASC X-ray facilities, of course, and Electra, where we collected many of these. With that, I come to the end of my talk. Thank you very much, and I suggest that you all stay safe and be healthy. And this is a picture which I took about a few weeks ago. This is where I am protected, and you see that we are all very safe. We are all smiling, and hopefully you will all be the same with this COVID-19 being a nuisance at this particular point. Thank you very much.
Thank you. So the topic is open for questions.
I don't know how much they heard because there is a lot of backlash.
No, sir, it was clear. If anybody has questions, please unmute yourself and please ask.
Hello, sir. Can you hear me?
Sure,
Yeah,
go ahead.
Yeah, go on.
Sir, like what are the challenges when sodium is replacing lithium?
One of the possibilities is, of course, a very good question, sodium replaced by lithium. In fact, in the early days, my student Dipankar Saha did try this replacing sodium by lithium. And it so happened that the electrochemical procedures which we followed at that particular time were not successful. But I think it's a good idea that some people can try by substituting sodium by lithium. The issue is we could also try partial substitution of sodium by lithium. This is something which will be also very useful in my opinion, because the thing is, it's an open challenge. This can be treated, and I think electrochemical processes are available where we can replace the ion sodium by any other element. And so this is something which is very interesting. Thank you for the question.
Thank you, sir.
Hello, sir.
Yes.
Yeah.
Go ahead,
Yeah, sir. Likita yes has posted a question, sir, in YouTube. Zinc ion batteries are quite compared to lithium ion, and it's eco-friendly. So compared to lithium ion, they occupy less space. Why can't they be used?
Okay.
Is it clear, sir?
There is amount of. Sorry. Go ahead. Shall I answer?
Yes, sir. Yes, sir. Please.
Okay. This is for Likita, right? Okay. So the zinc ion batteries are still under considerable amount of research. There are people who actually practice this, and in fact, this. Am I on?
Yeah, you're on. You're on.
Okay, the PPT went off, so.
Yeah. Yes, sir, we can hear.
Okay, so the answer to this question is that yes, zinc-based battery materials are being used these days, in particularly in fuel cells and so on. The thing is that the question of lithium batteries, as I already mentioned in the introductory part, the advantage of lithium is its size. And so it's small in ionic size, and also it is its conductivity properties are much superior to any element which is available with us at this moment. So with the use of zinc ion in batteries, it is indeed something which has to be experimented, and people are working on zinc based battery materials. The source of zinc, which is of course environmental friendly, can also be explored. And in fact, we could look at the minerals which contain zinc, or replace sodium with zinc. That is also a possibility. So there are umpteen possibilities to open up. You see, now we are in fact looking at, as I mentioned, it is an Aladdin cave. So we could rub on the lamp anytime with any element and see what happens.
Sir?
There is a second question coming from Shanti Matthew. He's asking, like, material exhibit polymorphism. Are they also exhibit polytypism?
Very good question. This is a general question. See, polymorphism is a property which comes to a given material when it crystallizes. It crystallizes in more than one form. On the other hand, the polytypism is an issue which is something to do with the structural framework. So polymorphism and polytypism are two different issues. And in fact, we have an article on polytypism, the paper written by myself and Amol Dekundwar several years ago, which clearly brings out the difference between polymorphism and polytypism. I would suggest Shanti to look at it. At the same time, there is a very old book on polymorphism and polytypism, which is available. And this was a book written by one of our early scientists from India. I think there is a lot of articles from P. Krishna on this issue. And Verma is the author of this book, Polymorphism and Polytypism, by Professor A.R. Verma. That discusses the issue of polytypism in detail. So I suggest Shanti to look at this.
Sir, there is a question from Arpita. How can we identify isostructural compounds?
Okay. The way in which we identify isostructural compounds is to do X-ray diffraction studies. And when we do X-ray diffraction studies, the isostructurality will produce identical X-ray diffraction patterns. So suppose let us say we have suppose we say we have any or the CD is replaced by MN, then we will see the isostructurality when we record the powder diffraction pattern. The two patterns will be exactly the same.
Hello.
Yes.
Yeah. Hello, sir. There's a question coming from Shakuntala. Can you suggest some eco-friendly batteries for future days?
It's a very interesting question because I think the current day batteries are eco-friendly as we believe, and that's how we are surviving. And for the future, eco-friendly batteries probably will be from a biological source. This is what I believe, but I'm not sure of how to answer that question. Hello.
Participants, please mute yourselves. All participants, request you all to mute.
So may I
There's a question from Mr. Bharat.
Yeah.
Hello?
Carry on.
So can you hear me?
Yeah. Go on. Yeah.
Go
We
ahead.
can hear you. Please ask.
Hello, sir. Can you hear me?
Yeah.
Go ahead.
There's a question from Mr. Bharat. He says, doped graphene materials are also good ionic conductor and also graphene batteries. Why graphene-based material is not used? That is the question.
So the issue is to worry about the production costs and so on. And obviously, graphene-based materials could probably be costing $1 million. And probably that's the reason why they are not used yet. I'm not sure how to answer this question. But the graphene-based materials could be reliable materials in the future. But making these materials is a challenge, and that involves a lot of high-quality chemistry which has to be done. The chemistry which we have used is very simple. In fact, I must confess that I am not a chemist, I am a physicist. And therefore, my chemistry is very limited. And with the limited chemistry, we can make these materials. And that's what it means. I mean, so making these materials would be a very serious challenge. I suppose it answers the question.
Sir, there is one question coming from Moti Krishnan. Are all these materials show non-linear optical behavior?
This is interesting because it so happens that most of these materials which we have studied, as I showed examples as well, they're all centrosymmetric. And since they're all centrosymmetric crystalline materials, they do not show nonlinear properties. So if we want them to show nonlinear properties, we have to make some modifications on these. And that would be a very interesting challenge. And if we get non-centrosymmetric crystalline materials, then it will show nonlinear optical properties.
Hello. Sir, am I audible?
Yeah, go ahead.
I'm Jivika from St. Joseph. I had a question actually. In one of the fast ion conducting materials which you had discussed, you were replacing manganese from with cadmium.
Replacing manganese with, sorry?
Cadmium.
Okay, okay.
So, will there be a difference if we use different transition elements in the conduction of sodium?
Yes, it's a good question. In fact, the presence of different elements would make small little changes, not enormous changes, because the sodium coordination with these elements is still the same, except that the distances of sodium to these elements probably would be sorry, the probably would be issue which will come up. So their property, the conductivity's behavior will be slightly different, but not enormously different. So you can substitute these. Now, once again, when we worry about cadmium, cadmium is also not a very environment friendly material. So we need to worry about that. There's a lot of possible experiments that can be conducted.
Thank you, sir.
Thank you.
There is one more question from Mr. From Dylan from SJC. He says, if there is any more time, is a lack of lithium contributed to the major use and lack of cobalt? Because lithium cobalt batteries are used in mobile phones. To get the question. So, is the lack of lithium contributed to the major use and lack of cobalt? Don't get the question.
I think I don't get the question fully, but I think what is meant is that possibly the presence of lithium in lithium cobaltate or something like that.
Lithium cobalt batteries are used in mobile phones. That's what he says.
Okay. Yes, the question is once we end up with the supply of lithium in terrestrial sources, then the lithium cobalt batteries used in our mobile systems would cease to exist. And so we need to replace those by new materials. And that is the idea of looking for new materials. I hope it answers the question.
Sir, there is one more question. The participant is asking, sir, I have heard that the mobiles before had a memory built-in battery. If we charge it for a longer time for the first time, so that it lasts that long later. Should I repeat, sir?
Yeah, please.
I have heard that the mobiles before had a memory built-in battery. If we charge it for a longer time for the first time, so that it lasts that long for the rest of the use.
I'm not aware of this. I don't know whether I have an answer to this question.
Okay.
So, Ronald, shall we close the meeting?
Sir, from YouTube team, so there are around 850 plus participants here and another 100 plus participants in webinar. all YouTube participants now are very happy with your session.
Oh, thank you.
Yeah, they're thanking you, sir. They're thanking you a lot.
No, unfortunately, I'm sorry. The voice didn't come through the way it should have come through because of some backlash. I don't understand why it was there, but it kept repeating whatever I said back to me. So I hope it was all very clear to people. I'm
Initially, there was
thankful
a problem,
to everyone.
Yeah, initially there was some problem, but the session went on well.
Oh, thank you. Thank you. Thank you very much. Yeah, I'm seeing a lot of thank yous coming up on the screen. So.
Any other questions, please?
What I suggest is they can write to me. I'm anyway free. The COVID-19 has locked me up here, so I will be able to answer them on the email. So people can ask questions on the email.
So if there are no other questions, may I request Dr. Nalini to propose vote of thanks?
Yes, sir. Good evening, everyone, and good morning to Professor Guru Rao there in Buffalo. On behalf of our HOD and faculty from the Department of Chemistry, St. Joseph's College, I'd like to thank Professor Guru Rao for this informative and very interesting webinar. It was nice to know that some little work that I did was taken over by many students and much progress has been made. I'm also grateful that he was able to adjust his timings to address this from a different time zone. As you know, he's presently at Buffalo, and like HOD said, it's morning 8:30, I think now. Yeah, I guess. I'm grateful to our HOD. Sir?
It's almost 9:30.
Oh, okay. I'm grateful to our HOD, Professor Ronald Mascarenhas, for being the force behind organizing this international webinar. And the response has been very good and we're very happy about it. I'm thankful to Dr. Suhas from our department for taking care of the technical aspects of this webinar. I think till yesterday they were all working very hard so that this can be streamed on YouTube to all the number of audience, and so that the bandwidth also works. I also thank Mr. Neeraj, who's an EPS student who assisted him in this regard. A very special thanks to Mr. Neville from the Department of Mass Communication, St. Joseph's College, for going beyond his duty to help with live streaming and smooth running of this event. I'm very grateful for his immense help. I also thank the Department of Mass Communication of St. Joseph's College for their YouTube channel. We also thank Dr. Joyce from our department, St. Joseph's College, and Dr. Nagaraj Shetty, HOD, KLE Engineering College, Hubli, for all this their help with the webinar. Even as and when people couldn't hear or anything, immediately Dr. Joyce rose to the occasion and she was sending links, etc. Last but not the least, I'd like to thank the graduate students, postgraduate students, research students, faculty, and all the other audience from our college and other colleges in and around Karnataka, and also the world. So I think somebody also has been, two of my students, one of them is in Germany, another one is in Belgium. They're also watching, I hope so, for attending this talk. Thank you very much. So like Professor Guru Rao said, he's quite open. I think you can always ask questions on through his email, which is web, and so it's thank you, sir. So it was a wonderful experience. Thank you.
Thank you very much, and I'm sorry that it went a little slower.
No, sir, it was fine, sir. It was fine.
It is not one of my usual high flowing talks. So it so happened that it went back and forth a little bit. And I was getting a reflected voice back.
I think you got echo. Yeah, I think you had
and that was very annoying. But anyhow, I hope I did not disturb the people to get a feel for what I wanted to say. All of us very much, and we will be in touch. Thank you, Ronald. Thank you, Nalini.
Yeah, all of us.